Okay, let's dive into this chemical mystery.
So what we're looking at here is something called a titration curve. You can kind of think of it like a chemical fingerprint. It's a detailed play-by-play of a reaction from beginning to end. And our job, we're going to read the story it's telling us. So how do we solve this? Well, we're going to have to put on our detective hats. We're going to examine all the clues that are hidden right here in this graph, piece by piece, until we've unraveled the whole shebang. All right, first things first. Any good detective knows you have to start by identifying the players involved, right? So let's dig into the evidence here in the graph and figure out exactly what our reactants are. And here we go. This is our lineup of suspects. We've got 3 possible pairs of chemicals. The big question is, which one of these reactions does our graph actually show? You know, the key to cracking this whole case is just a few simple visual clues right here on the graph. Just by looking at the shape of the curve, we can start to narrow down our suspects. So let's break down exactly what we're looking for. Okay, look where the story begins. The pH starts way up high, well above 7. That's a dead giveaway. It tells us the chemical that's already in our beaker, what chemists call the analyte, it has to be a base. Then, as we add the other chemical from the dropper, the titrant, you see the pH drops. Well, what makes pH drop? An acid. So that immediately rules out titrating an acid with a base. Suspect number 1, gone. Now here's the really crucial clue. Do you see those 2 super steep drops in the curve? Each one of those is what we call an equivalence point. It's a moment where a step in the reaction is totally complete. And having 2 of them, that means our base is diprotic. That's just a fancy way of saying it reacts with the acid in 2 separate, distinct steps. So let's put it all together. Based on all the evidence, we started with a base, we added an acid, and we saw 2 reaction steps. We've unmasked our reactants. The chemical in the beaker is potassium sulfite, which is a weak base, and we're titrating it with nitric acid, a strong acid. Boom, case closed on that mystery. Okay, so we've identified our chemicals. Let's keep going and see how this whole story builds. Now that we know who our players are, let's go find our first piece of hard evidence. That starting pH value. Let's calculate it. So before we've added even a single drop of acid, what determines the pH? Well, it's a process called hydrolysis. It sounds complicated, but all it means is the sulfite ion from our base actually reacts with the water itself. It grabs a hydrogen from a water molecule, and that leaves behind hydroxide ions. And that is exactly why the solution is basic to begin with. To really nail down that starting pH value, we're going to follow a little 4-step investigation. What we're really trying to do is figure out just how strongly our base reacts with water. This means we'll find a value called the base dissociation constant, or Kb. Then we'll set up something called an ice table to track everything and then solve for the pH. It's pretty much the standard playbook for this kind of problem. And after we run the numbers, we get a starting pH of 11.4. This is perfect. It confirms exactly what we saw in the graph. We absolutely started with a basic solution. Our first data point is locked in. All right, let's talk about the equivalence points. These are the most dramatic moments in our whole story, right? Those steep drops where the chemistry just changes on a dime. Let's see what they can tell us about our titrant. So the graph tells us that the second big drop, that's the final equivalence point, it happens right when we've added exactly 40 milliliters of nitric acid. This is that magic moment, the precise point where we've added just enough acid to react with every last bit of that initial sulfite base. And that volume? That 40 milliliters, that is a critical clue. Why? Because we know the full reaction has a 1-to-2 ratio. In other words, it takes 2 protons from the acid to completely neutralize 1 sulfite ion from our base. We can use that relationship. This little bit of chemical accounting, it's called stoichiometry, lets us use the volumes we know to find the one thing we don't know, the concentration of the acid. And there it is. The concentration of our nitric acid titrant is 0.25 molar. Another key piece of the puzzle just clicked into place. So let's pause for a second and take a mental snapshot of the beaker right at this exact moment. 40 milliliters of acid have been added. What's actually floating around in there? Well, we've got potassium and nitrate ions. They're just spectators, kind of watching from the sidelines. But the crucial part, all of our original base, the sulfite, has now been completely converted into its acidic form. Sulfurous acid. Okay, time to investigate the final act of our chemical story. What happens when we just keep going? When we push right past that final equivalence point and start adding an excess of acid? So at this point, after we've added 50 milliliters,
All of that original sulfite base is long gone. It's been completely neutralized. The only thing that's controlling the pH now is the extra, unreacted strong acid we dumped in during those last 10 milliliters.
And you know what? Calculating this final pH is actually pretty simple. Since the original base is totally gone, all we have to do is figure out how much extra acid we added in those last 10 milliliters. We'll calculate the moles of that excess acid, divide it by the new total volume of our solution, because we've been adding liquid, right? And that gives us its concentration. Then, boom, a quick calculation gives us the final pH. And the final number we get is a pH of 1.55. That puts us way down in acidic territory, which, if you look, is a perfect match for the very bottom of our curve on the graph. It all lines up. And just like that, the mystery is solved. By carefully following the clues, the shape of the curve, the starting pH, those critical equivalence points, and the final pH, we have completely decoded the entire chemical story being told by this one single graph. It's just a fantastic reminder, isn't it, that sometimes the most complex information is hiding in plain sight. A simple curve on a graph can hold so much data and tell a really complete story, as long as you know the language it's speaking. Makes you wonder, what other hidden stories are just waiting for us to decode in the data that's all around us?